We begin with speech processing, a new topic, which is one of the most important applications of hidden Markov models, except that instead of discrete outputs, the HMMs shall be continuous. So this is a discrete output HMM. It's a 5-tuple. Theta equals set of states, set of output symbols, the state transition matrix P, Q is the emission matrix, which is the probability of emitting output symbol K from state I, and pi, which is the initial state probability vector. So continuous output HMM, we define the HMM theta as the set of states, and the set of outputs is going to be quite different. In the discrete output HMM, the set of output symbols was a discrete set, and each output was a discrete symbol, A, B, C, D, and so forth, for example. But this time, each output is a d-dimensional real vector. So that's B here. And the state transition matrix is the same as before. And here's how we characterize the emission probability. QIV is the PDF of the output vector V given the state is SI. So this is the PDF of V, and that is modeled as a Gaussian mixture model. Summation CIM times the Gaussian distribution N of V given mu IM lambda IM. I'm using lambda IM for the covariance matrix in place of sigma IM to avoid confusion, because we will be having summation so many times. And pi, the initial state probability vector, remains the same as with discrete output HMMs. Now, since the output symbols are completely characterized by the GMM parameters, so we actually don't need to include V, the set of output symbols, in defining the HMM. So that's completely characterized in terms of the GMM parameters, which are CIM, mu IM, and lambda IM. And remember that we have a separate Gaussian mixture model for each state I. So here is the Gaussian mixture model for each state I. So this is the PDF QIV, and that's a mixture of Gaussians. Each Gaussian has a mean and a covariance matrix, and CIM is the probability that the mth Gaussian will be active in generating the output, and that's also at state I. And so QIV is summation of CIM times the normal distribution, and M is the total number of Gaussians. We assume that for each state I, the total number of Gaussians remains the same. And of course, V given mu IM, lambda IM is the usual expression for the Gaussian distribution. And now, since this is a vector, I am using bold. However, I'll still use italics because the straight V will still represent the V1, V2, V3 up to V uppercase T, the continuous output sequence. Now, CIM is the probability of the mth Gaussian being active, and therefore summation m equals 1 through uppercase M, CIM must equal to 1. And this is the output sequence, V1, V2 until V uppercase T. So here is the GMM for each state I, where I is between 1 and n. N is the total number of states. And QIV is the emission probability distribution function, PDF, of the output vector V, and that's modeled as a summation of Gaussians. In this figure, it's a summation of 3 different Gaussians. Ci1, Ci2, and Ci3 are the probabilities of the first Gaussian, second Gaussian, and the third Gaussian being active in generating the output vector V. And the means of the 3 Gaussians are mu1, mu I1, mu I2, and mu I3. Now, again, as a reminder, each state will have its own GMM with m Gaussians. The learning is as before almost. So we have the set of states which is known, and we are given output sequence V, or multiple output sequence actually when doing speech processing. And our goal is to find theta ML using maximum likelihood estimation, and that's theta star, and theta star is the max likelihood of containing P star, the state transition probability vector matrix, CIM star, mu IM star, and lambda IM star, which are for the Gaussian mixture model, and pi star. And I is the total number of states, I is the index of states, which is between 1 and n, and m is an index for a Gaussian, and that's between 1 and m. And our approach shall be, as always, the EM algorithm. Now, in discrete HMMs, we had this variable defined, gamma Ti, which was the probability of the state being Si at time t given the output sequence V. That's gamma Ti. Now, in the continuous situation, it's going to be similar, but with some important differences. So for the continuous HMM, we define gamma TIM as the analogous variable. So gamma TIM is now defined as the probability of the state at time t being equal to Si, and the Gaussian that is active is the mth Gaussian. So the mth Gaussian is active when the state is Si, and that's at time t given the output sequence V. Now, this probability of St equals Si and the mth Gaussian being active given V can be factored as follows. So this is probability of St equals Si given V times the probability of the mth Gaussian being active given St equals Si, comma, V. Now, we already know alpha Ti is the probability of the output sequence from t equals 1 through the current time t and st equals si. That's alpha ti. We have seen this in the forward algorithm. Similarly, when we discussed the backward algorithm, we defined beta ti as the probability of the future output sequence v given the state at time t is si. This is the difference which you are already familiar with. This is a joint probability of the past and present output and the state st equals si, but this is a conditional probability of the future outputs given st equals si. That's the condition, st equals si. Their product, we have seen this before too, alpha ti times beta ti is, now I take v of 1 through t and v of t plus 1 through uppercase T here, and st equals si. That's the joint probability, alpha ti, beta ti. And since this is the sequence of output vectors until time step lowercase t, and this is the future output sequence t plus 1 through uppercase T, so I can concatenate them to give rise to this vector v. This is the full output sequence. And so alpha ti beta ti is equal to the probability of the complete output sequence v and the state at time t being equal to s sub I. Therefore, if I sum over all these states, I get probability of v. This is based on the summation trick that we had seen earlier. If I sum over this index I eliminate this component of the probability. So this summation I equals 1 through n of alpha ti beta ti, I eliminate I here, and that gives me simply probability of the entire output sequence v. Now, what's the ratio? Alpha ti beta ti is the probability of the output sequence and st equals si, and summation I equals 1 through n of alpha ti beta ti is simply p of v. Therefore, the ratio, the numerator is the probability of v comma st equals si, and the denominator here is simply p of v, and so this ratio is the probability of st equals si given the output sequence v. Note the difference. This is the joint probability here. The alpha ti beta ti product is a joint probability, but when I divide it with this summation, I get the conditional probability. So the conditional probability pst equals si is given by alpha ti beta ti divided by summation alpha ti beta ti. And that's the same thing as this factor in gamma tin. So we already defined, or rather derived, an expression for this factor in gamma tin in terms of alpha ti and beta ti. And now we have to find this factor, which is p, the probability of the mth Gaussian being active when the current time step is t and the state is si. So st equals si and output vector v, output sequence v. So now this is gamma tim, and we factored it into two probabilities. The first probability we already derived an expression for, and now we are going to derive an expression for the second factor here, which is the probability of the mth Gaussian being active given St equals Si and the output sequence V. Now, since each state I has its own separate GMM, this condition need not be over the entire output sequence V. It can only be V at the specific time instant t. Therefore, the second factor is simplified as this. This is the only difference. Instead of V, I have Vt here, and that's because this mth Gaussian being active is only when St equals Si. Now, Cim is the probability of the mth Gaussian being active given Si. I've just used a shorthand notation. This is the same thing as St equals Si for any given time instant t. The Gaussian PDF V given mu Im lambda Im is the probability of V, or the PDF of V, given the mth Gaussian distribution is active and the state is St equals Si. If I multiply Cim and this PDF, now I have St equals Si in both places as part of the condition, and so this becomes the condition here, St equals Si, and this is the probability of the mth Gaussian being active, and this is probability of the output V of t given that the mth Gaussian is active. And so this becomes the joint probability of V of t and mth Gaussian being active. Now I apply the summation trick. So I will sum over m, so I will get rid of this component of this probability. And so this becomes equal to summation of Cim times nVt mu Im lambda Im is equal to, after I get rid of the mth Gaussian being active, I'm left with V of t and St equals Si here as the condition. Now I take the ratio. The numerator here is Cim times n of Vt given mu Im sigma Im, lambda Im, and the denominator is summation over the same thing. So what we have here is, in the numerator we have the probability of V of t given the mth Gaussian is active and St equals Si, and the denominator is simply P of Vt. So the numerator once again is the joint probability once we take into account the St equals Si, which is the condition in both cases. The numerator is the joint probability Vt and mth Gaussian being active, and the denominator is simply Vt. Therefore, the ratio is equal to probability of the mth Gaussian being active, and this Vt becomes part of the condition. So now we are left with this expression, probability of the mth Gaussian being active given St equals Si, comma Vt equals this expression here, and if you compare it with the second factor of gamma Tim, they are both equal. Therefore, we have obtained an expression for gamma Tim. Since we already have an expression for the first factor here, and now we have just obtained an expression for the second factor, we have completed an expression for gamma Tim. Now, one thing to note is that this probability of V given St equals Si is nothing but the emission PDF, Qi of V. Now we are ready for the E step, and we will estimate each parameter of the Gaussian mixture model separately. So now let's focus on CIM estimate, which is the probability of the nth Gaussian being active when the state is S sub I. Now we already derived an expression for gamma TIM. Let's look at the definition of gamma TIM once again. It's the probability that the state at time t is Si and the Gaussian, the mth Gaussian being active, given the output sequence V. What CIM? CIM is simply the probability of the mth Gaussian being active given the state is Si. Now, this does not have the V here because this is the generic expression for CIM, but when we do the estimate C hat of IM, then we must add V because we are estimating only for this sequence V. So this is what we have. CIM is this probability of the nth Gaussian distribution being active when the state is S sub I, which implies that the expected number of times the HMM is at Si and the mth Gaussian being active given V from this expression is equal to summation gamma of TIM. What I've done here is I've eliminated the time T here through this summation trick. And therefore, what I have here is the expected number of times the HMM was at state S sub I and the mth Gaussian was active. This mth Gaussian, as a reminder, is different for each state I, and so it has its own separate parameters. Let's remember that. Anyways, back to this expression, the expected value is summation gamma TIM. Now, the expected number of times at Si given V is equal to this double summation here, T equals I through uppercase T summation, summation M equals through uppercase M of gamma TIM. Again, the summation trick here, what I did here was I eliminated the mth Gaussian being active condition here by summing over the Gaussians M. So what I have here is expected number of times at Si given V, and here what I have is expected number of times at Si given, and mth Gaussian being active given V. The only difference is the mth Gaussian being active here. So the ratio is the numerator has this number of times at Si and mth Gaussian being active, and the denominator has number of times at Si simply. And so the ratio is the probability of the mth Gaussian being active given Si. And that's equal to the estimate of CIM. Now let's see how to obtain estimates for the GMM parameters mu im and lambda im. We already know that gamma TIM is the probability of ST equals SI and the mth Gaussian being active given the output sequence V. Mu IM is the expected value of the output vector given ST equals SI and the mth Gaussian is active. That's the definition, which is equal to this summation here. Now, before I go over this summation, let's look at an explanation. This is a highly intuitive explanation. Now, we all know that the average value of x, if we have different samples xk for k equals 1, 2, 3, 4, and so on, is given by this expression. Summation k, probability of xk times xk divided by summation k of pxk. Here xk is a off-on or a Boolean variable. That's true or false. Now let's say we have another variable y which is dependent on xk. And so the expected value or the average value of y is given by this expression here, summation k pxk times y of xk divided by summation k p of xk. I suppose this is clear. Now I'll draw an analogy with the situation that we have on the left. Now the samples k equals 1, 2, 3, 4, that index I'm replacing with I for the ith state and m for the mth Gaussian. And xk is the event st equals si and the mth Gaussian is active. Remember, it's a Boolean variable. So it's either true or false. And y of xk, y is a function of xk, so that is equal to, that is analogous to the output vector when st equals si and the mth Gaussian is active, which is v of t. So if you compare this here with this, now let's see, instead of these probabilities p of xk, what I have is the probability of st equals si and the mth Gaussian being active. And I'm summing over all times. And during each time, I know that one state is where the HMM is, which is state I, and one Gaussian, the mth Gaussian, for state S sub I is active. And so this P of xk I'm replacing with this probability here, and I'm summing over all times t. And this y of xk is this output vector here at time step t, and the denominator is simply summation of the probabilities. Another simpler way to look at it is pretend that these probabilities are the weights, because we are looking at state I and output Gaussian n. And so this is summation of P of st equals si mth Gaussian being active, which is the weight for that index pair I and m, and the denominator is summation of the weights. Now comparing it with gamma TIM, so these probabilities are actually nothing but gamma TIM. Therefore, what we have is mu im is directly from this expression here, we get the expression mu im estimate equals summation t gamma tim times output vector V of t divided by summation t gamma ti m. And lambda im estimate is obtained in a very similar manner. All I'm doing is replacing v of t with vt minus mu im times vt minus mu im transpose. And that gives me lambda sub im.